everybody, welcome back to another episode of the problem solving series. Today's video is going to be part one of looking at rotational dynamics and uniform circular, I guess not necessarily uniform, but circular motion. In this video, I want to go ahead and cover how we can think about the coordinate system when we're dealing with circular motion problems, and also the rotational kinematic equations and going from those angular quantities to linear quantities. So I'll talk all about that in this video and go through an example as usual. And then in part two, I will go ahead and cover centripetal acceleration and centripetal forces and how those come into play with our circular motion problems as well. So without further ado, let's just get into things. So up until this point, we've mainly been thinking about motion that even though it can happen at an angle, we have things occurring linearly along the x dimension and the y dimension, and we've split up our space into these two axes that are perpendicular to one another. And if you have an x component and a y component, or an xy coordinate pair, you can describe any point in two-dimensional space. But that's not the only way that we can split up and kind of set up this grid to define points in 2D space. If you remember from a million years ago, which honestly I can't even remember what math class I learned this in, maybe algebra 2, maybe geometry, whatever. We can also use the polar coordinate system, and that's going to be especially useful when we're dealing with angular or rotational kinematics. So the way that we would do that is that if we have a circle drawn first on an xy plane, we could, like I said, define that point as an x coordinate and a y coordinate. But if we're moving along this circular trajectory, that's not necessarily the nicest way we want to write it. So instead, we can write it in terms of the radial component, or radius r, and the angular component theta, which is defined from the positive x-axis. Just a note on sign convention here. Typically, we think of pointing towards the center as positive and away from the center as negative in physics context. And then we typically, as far as angular quantities go, think about counterclockwise as positive and clockwise as negative. So those are good things to keep in mind for later on, especially. Hint, hint, when torque is coming. Then as far as the angular kinematic equations themselves, they're of pretty much the same structure, except for subbing out the angular quantities for the linear quantities, as you've been working with in projectile motion and 1 and 2D kinematics. So theta is going to be our angular position. Omega, which looks like a lowercase w, is going to be our angular velocity, and then alpha is going to be our angular acceleration. The other frame of mind that we can look at circular motion that can come into play is going to be thinking about radial and tangential instead of radial and angular. And all that means, so a tangent line to a circle is that at any point you can draw a line extending out straight. So if you were instead to stay along the curved path, you keep going straight, that would be the tangent line, and it's perpendicular to the radial line. So again, I'll have a picture of that up here so that you guys can see that and see what it looks like. And again, depending on the context of the problem, you might want to use this tangential centripetal axes instead of this angular and radial axes combo. In order to get from angular to tangential, because they are related, you would just multiply by the radius. So again, this might be pulling from knowledge far, far back, but arc length, or the length that you've traveled along the circle, is going to be equal to the radius times the angle that you've traveled through. The tangential velocity will be equal to the angular velocity times r, and the tangential acceleration will be equal to the angular acceleration times r. And that will all be up, probably covering me, so that way you can see it and screenshot it if you need to, and then keep those for your equation sheets. The only other topic, or concept I guess I should say, that I want to touch on before moving on to the example problem is the idea of a period. So we define the period as the time that it takes to complete one revolution. This is typically denoted by a capital T. So now we're also kind of getting into multiple things being defined with the same variable. So if you're not using F sub capital T for your force tension and just using capital T, now we have two capital T's. That means something completely different. So labeling and bookkeeping and keeping your variables organized will be really important, especially, it should have been important before, but even more so going forward as we get repeats of these variables being used. And then, oh my God, what was I about to say? So we've got period, and then the other thing is that 1 revolution, we can convert that to angles, so that would be 360 degrees or 2 pi radians, or 1 full circumference, which would be 2 pi times r. I think I didn't mention this, but all the angular quantities that we want to use are going to be in terms of radians. So theta is in radians, not degrees. Omega is radians per second, and alpha is radians per second squared. Now that I've kind of gone through all of that, let's jump into an example problem, and I'll also show in this problem some of the common tricks that they throw in to just add complexity.
Okay, an object is sitting on the edge of a disk with diameter of 4 centimeters that spins at 30 rotations per minute, that's RPM. After 5 seconds, what angular distance has it traveled, and what is the linear velocity of the object? So I have gone ahead and written this problem so that it has a lot of the common elements that I think get thrown in to angular kinematics or rotational kinematic problems, or really just rotational stuff in general, that are there to kind of trip you up and that you're just copying down numbers, and if you're not careful to pay attention to what the numbers mean, then whatever you plug in won't be right and you'll end up with the wrong answer. So the first thing is that they're giving us the diameter when most of the equations that we have are really interested in radius. And they gave us that diameter in centimeters, and we're going to want that in meters. So first I'm going to just go ahead and take care of that. So if we have the diameter equals 4 centimeters, radius is 1/2 of the diameter, so radius will be diameter over 2, which will be 2 centimeters. And then we'll go ahead and convert that to meters by saying 1 meters over 100 centimeters is technically equal to 1, since those are equivalent. And then the centimeters cancel, and we end up with 0.02 meters for our radius. The other value that I gave you, that RPM, is going to be technically, so I would technically say that this is a angular frequency because it's rotations per minute or cycles per time, which we typically think of as a frequency, but you guys haven't really been introduced to that concept. So we can think about it instead as our omega. So our omega is going to be that 30 RPM, but since that's technically in revolutions per minute or rotations per minute, we want that in radians per second. So we're going to use first that there are 2 pi radians in 1 revolution, and then we'll also use 1 minute divided by 60 seconds. And oh, I didn't even plan this. That ends up being 3.14 radians per second. And then the last given we have is going to be our time. So we have t equals 5 seconds for the first question that we're being asked. So we're going to solve for the angular distance it's traveled if we assume that our initial position we'll call 0, which is pretty standard. I also didn't say, but we can assume that since it says that it's spinning at this rate, that we don't have an alpha in this case, so our alpha will also be 0. Then when we go ahead and write down our equation for angular position, theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Subbing in just the things that are 0, we'll end up with omega naught t, and that would be the same as our omega since that's constant. So then it's pretty simple and straightforward. We'll put in this 3.14 radians per second times 5 seconds, which will give us 15.7 radians as the total angle that we travel through in that 5 seconds. So that would be part A. Then part B is asking what the linear velocity of the object would be. So we're going to do a conversion from an angular quantity to a linear or tangential quantity. And for that, we'll use our tangential velocity, which most of the time they leave that t off that I wrote. So V is omega r. Our V is going to be 15. Oh, nope. It's going to be 3.14 times 0.02, which was our radius, which will be 0.0628 meters per second.
Oh my gosh. Look at you. You're stunning. Ah! And you're sleepy. Say bye to the kiddos. I'm gonna go take a nap.